Okay, consider this. Calculate the reactions for the beam below. And you see the beautiful drawing here? I would consider this a cantilevered structure. It looks like there's a cantilever between D and E, between B and C. Okay, I noticed that I have two hinges here at C and D. What is a hinge anyway? If I've got a hinge, at those hinges there'll be a vertical and a horizontal reaction, but no moment reaction. I can actually disassemble this beam into three different parts: AC, CD, and DF. But before I do any of that, what are the external reactions? Notice that I have three rollers and a pin. Okay, so I've drawn all the reactions in here. At A, there's a pin, so I've got two reactions, a horizontal A sub x and a vertical A sub y. At B, I've got a roller, so I have one reaction, B sub y. At point E, that's a roller, so one reaction, E sub y. And then at F, it's a roller, so one reaction, F sub y. Okay, remember the equilibrium equations? The problem is that there's too many reactions for the equilibrium equations to be useful, and I challenge you to try that. But if I attempted to solve this using our three equilibrium equations, there would still be too many unknowns. However, I do have the option of dismantling this structure and drawing three different free body diagrams. So the first thing I'm going to do is unbolt it at C, unbolt it at D, and draw a free body diagram just of portion CD, which is bounded by the two hinges at C and at D. Okay, here's portion CD. I cut out CD. Okay, now when I remove portion CD, anywhere where there's a hinge, there's going to be a horizontal and vertical reaction. So at C there was a hinge. Notice that I put a horizontal reaction, a vertical reaction. At D there was a hinge, so horizontal, vertical. Okay, well, if I say the sum of the forces in the x direction is 0, I'd have C sub x is equal to D sub x. Okay, well, too many unknowns. What about the y direction? C sub y plus D sub y minus 80 is 0, and too many unknowns. Take the sum of the moments about point C. Take the sum of the moments about point C, and you can find D sub y. And like magic, I do it. The sum of the moments about C is 0. Negative 80 times 3. Negative 80 kilonewtons. 80 kilonewtons, that's about 18,000 pounds. I say negative 80 because notice that this 80 tends to want to rotate it clockwise, and I'm considering counterclockwise positive. So negative 80 kilonewtons times the moment arm, 3 meters. 3 meters, that's about 10 feet. Plus the D sub y, unknown, times moment arm 6, distance between C and D, 6 meters, about 20 feet. That's equal to 0, so I get D sub y is 40 up. So let me draw that on my figure. 40 kilonewtons going up. So what about C sub y? The sum of the forces in the y direction is 0. Okay, so what does that tell me about C sub y? And like magic, the sum of the forces in the y direction is 0, C sub y up, minus 80, 80 is down, plus 40, so it's the D sub y, is equal to 0. So I find that C sub y is 40. I suppose I could have determined that by inspection. Notice that CD is symmetric. CD is symmetric about 80, so I just could have divided the 80 by 2, I suppose. Okay, what about C sub x and D sub x? Well, I don't know. Too many unknowns. So let me put this slide off to the side for a moment and go back to the original slide. I've examined CD. Now I'm going to examine portion DEF. And notice I've got this 75 kilonewton load acting at an angle. So now examine DEF. Okay, so I've separated out a member DEF. Go back to the original drawing. DEF. Okay, cut that out, take it off to the side like so. Okay, so at E and F I've got rollers, so vertical reactions. Those are still undetermined. Notice what's happening here at D. Okay, so here's DEF. I'm going to bring back the previous slide. Okay, here was CD. Okay, so what's happening here with CD? So they're right next to each other here. Okay, you see from my analysis of CD, dy goes up 40. So that means when I analyze DEF, I've got dy pointing down 40. Okay, notice equal and opposite here. Okay, dy going up as related to member CD, as related to DEF, dy going down. Okay, look at dx. When I analyze CD, I had dx pointing to the left. That means for member DEF, it'll be pointing to the right. Okay, for every action is an equal and opposite reaction. Okay, so I already know the d sub y is 40. I don't know d sub x yet. You see that 75? I'm going to break it up into horizontal and vertical components. Okay, and I do that. I replace the 75 at 30 degrees with horizontal 75 cosine 30 and vertical 75 sine 30. And I crossed off the 75 here because I'm replacing this 75 at 30 with horizontal and vertical. Okay, so now why don't I take the sum of the moments about point D and see where that takes me. Okay, sum of the moments about point D is 0. So 3 e sub y. I actually put the moment arm first. That's the 3 meters. Times e sub y, that's the reaction. Plus 9. Okay, that's the distance. 3 plus 3 plus 3, 9 meters. Times f sub y. Here's f sub y right here. Minus. Okay, it's minus because I'm talking about the 75 sine 30 that tends to want to rotate this clockwise about point D. Minus 75 sine 30 times a moment arm of 6 meters. Okay, so let me clean all this up. 75 sine 30 times 6, I'll move that to the right side of the equation. Okay, and I clean it up. 3 e sub y plus 9 f sub y is 225. So I call that equation 1. I've got one equation and 2 unknowns so far. Okay, the next thing I'm going to do, take the sum of the forces in the y direction and set that equal to 0. So what have I got in the y direction? I've got 40 going down, that's d sub y. 75 sine 30 going down. Going up, it looks like I've got e sub y and f sub y. So 4 items to consider in terms of the y direction. So I'm going to write an equation for that. And like magic, it appears. So the sum of the forces in the y direction is 0. Negative 40 going down. E sub y going up. Minus 75 sine 30 going down. Plus f sub y going up is equal to 0. Clean it up and you get what I call equation 2. E sub y plus f sub y is 77.5. So I've got these 2 equations and 2 unknowns. I've got one more equilibrium equation. What about the sum of the forces in the x direction is 0? What do I have going in the x direction? D sub x and 75 cosine 30. So now the sum of the forces in the x direction is 0. And there it is. The sum of the forces in the x direction is 0. D sub x to the right minus 75 cosine 30, that's to the left, is equal to 0. Do some arithmetic. D sub x is 75 cosine 30. I get d sub x is equal to, this is the exact answer, 37.5 square root of 3, approximately 64.952. I'm going to preserve the exact answer, so come back here to my free body diagram. D sub x, 37.5 times the square root of 3. Okay, that's not an external reaction in terms of the overall structure, but that is the horizontal reaction at the hinge, 37.5 times the square root of 3. Okay, well, there's still a matter of e sub y and f sub y. So I'm going to take equations 1 and 2 and solve those simultaneously. I'll use a matrix to do that. Okay, so I set up this matrix based on equations 1 and 2. Do you know how I did this? The first row, 3, 9, 225. So go back to equation 1. 3e sub y plus 9f sub y is 225. I take the coefficients on the two variables, take the constant term, make that the first row. How did I get the second row? Okay, what was equation 2? 1e sub y plus 1f sub y is 77.5. Coefficient 1, constant term 77.5. Okay, so this is one way of solving a system of equations using matrices. I propose taking this to reduced row echelon form, which a graphing calculator can do. So I'm going to take this to reduced row echelon form, and that'll tell me what e sub y and f sub y are. Okay, so I take it to reduced row echelon form, and I get this. Okay, now if you remember from linear algebra, the first column represents e sub y, the second column represents f sub y. So reading the first row, it tells me that 1 e sub y is 78.75. That means e sub y is 78.75 kilonewtons. From the second row, 1 f sub y is negative 1.25. The negative just means that I assumed the wrong direction for f sub y. F sub y negative 1.25. So these are actually two reactions that I needed. So I'm going to go back to my drawing on the previous slide, my free body diagram. Okay, remember this? Okay, so e sub y, what is that, 78.75? Okay, and then I'll remember that it's kilonewtons. 78.75, and then f sub y. Okay, I show it pointing up, it's actually down, but I'll leave the arrow as is, and I'll just put a negative here, so negative 1.25. And then put a box around it so that later on, if you look at this, you'll realize that you had to come up with that. It was not given to you. Okay, so where am I in terms of this problem? Okay, go back to the original drawing. Remember this? So what did I do here? I analyzed CD, I analyzed DEF, and some of these I can write in. So E sub y, 78.75 kilonewtons, and then F sub y, negative 1.25. Okay, how was that? But I still have A sub y and B sub y, don't I? I don't think I've analyzed portion AB yet, have I? Portion AB. I haven't analyzed that yet. Okay, so one thing that I forgot to do. Okay, let me bring back this previous slide. Okay, this is the one that I just was working on. Okay, so I've got E sub y and F sub y. I've got D sub x. Let me go back to member CD. Okay, so bring back this slide. So if D sub x is 37.5 square root of 3, let's slide this over. That means that here, for CD, I've got D sub x is 37.5 square root of 3. Okay, now slide this over some more. That means that C sub x is 37.5 square root of 3. Okay, how is that? So now this is complete. Okay, so what do I have here? DEF is complete. CD is complete. And now I am going to analyze. Now I'm going to analyze the member ABC. Okay, take that part out and draw a free body diagram. And there it is, member ABC. Free body diagram of ABC. Here's the original drawing. I took out ABC, so I'm just showing this part. Okay, did I recopy that correctly? Okay, now some of this stuff I might already know. Go back to my analysis of CD. Remember this slide? So here's CD. Hinge C, I've got 37.5 square root of 3 acting to the right. That means that where it meets member ABC, which is what I'm going to analyze now, it's now pointing in the opposite direction, that is to the left. You notice this? For CD, it's pointing to the right. That means for ABC, it'll be pointing to the left. Okay, for every action, there's an equal and opposite reaction. So 37.5 square root of 3. Okay, how is that? Now what about C sub y? When I analyze CD, I had C sub y going up 40. Where it meets ABC, it's going down 40. Okay, so I'm getting those from my analysis of CD. Okay, so I've got 3 unknowns. Okay. Isn't it pretty obvious what A sub x is? Okay, I'm not even going to show the equation, but if you take the sum of the forces in the x direction as 0, then clearly A sub x, 37.5 square root of 3 kilonewtons. How's that? Okay, that 2.5 kilonewton per meter, I'm going to turn that into its resultant force. So multiply 2.5 by 11. 8 plus 3 is 11. And then apply the resultant at the middle, which will be 5.5 feet from A. Or not 5.5 feet, I mean 5.5 meters. So I'm going to do that now. And like magic, it appears. So I multiplied 2.5 kilonewton per meter times 11 meters, and I get 27.5 kilonewtons. The squiggly arrow means it's the resultant, and then I crossed off the 2.5 because I don't want to double dip. I want to be reminded that the squiggly arrow takes the place of the 2.5 kilonewton per meters. Okay, and it's acting at the midpoint of the distributed load, so 5.5 meters from point A, or from point C for that matter. Okay, so now I'm going to take the moments about point A. Moments about point A, counterclockwise, will be positive. That will leave me with B sub y as my only unknown in that equation, so now I'm going to do that. And there it is. The sum of the moments about point A is 0. Negative 27.5 times 5.5. The negative is because the 27.5 wants to rotate this portion clockwise about point A. So negative 27.5 times moment arm 5.5. Plus B sub y times 8. So B sub y is right here where the pencil is. Times moment arm 8 meters. Minus 40. That's the C sub y part. Moment arm 8 plus 3 is 11. Is equal to 0. So you can do the algebra and find that B sub y is 73.90625. So write that on here. Okay, that's B sub y. Lastly, I need A sub y. So just take the sum of the forces in the y direction as 0, and that is going to appear like magic in just a second here. And there it is. The sum of the forces in the y direction is 0, 27.5 going down, 40 going down. That's what you see here. A sub y going up, 73.90625 going up. I get A sub y is negative 6.4 approximately. If you get a negative, that just means that you assumed the wrong direction. So when I drew my free body diagram, I was assuming it was up. It's actually down. I'll keep the drawing as is, and I'll just put a negative in front. Okay, so that's A sub y. So now I'm going to transfer this over to my original free body diagram, the original slide. So I'm going to bring that back. Okay, remember this? Okay, so what have I got here? A sub x, 37.5 square root of 3. I suppose they should write kilonewtons on there. And then A sub y, if I'm going too fast, you realize that you can pause the video. You can pause it, you can rewind it, but you just can't ask questions in real time. B sub y is 73.90625. Okay. So I have all the reactions at A, at B, at E, and at F. So for this beam, I needed to break it up into 3 parts. I would not have been able to solve it given its original form, that is, without breaking it up. So what good did those hinges do? Okay, well, the hinges allow me to introduce new and independent equations in terms of the support reactions. So we would call those new equations equations of condition. The phrase equations of condition refer to additional equations in terms of loads and reactions. For example, the sum of the moments about hinges C or D. Okay, so an equation of condition would be, for example, the sum of the moments about point C. Another equation of condition would be the sum of the moments about point D. If the girder had been continuous, that is, if there hadn't been hinges at C and D, then by cutting it, I would have actually created a bigger mess because I've got hinges at C and D. I've only got horizontal and vertical reactions, but if those hinges weren't there, and if I were to just have cut it at C, for example, I would not have only had the horizontal and the vertical, but I would have also had an internal moment reaction. So if I had had a continuous beam, it would have created a bigger mess to have just arbitrarily cut it at either C or D. The fact that I've got a hinge there, the fact that I've got a hinge at C, a hinge at D, allows me to cut it and not make a bigger mess in terms of my calculations. Remember that a hinge carries no moment. How could I check all this? If I want to double check that I got the correct numbers, just take the moments about point A, or the moments about point B, for example. Take the moment about any point for the entire thing, for the entire structure. Take the moments about some point and verify that it does wind up being 0. Take the sum of the forces in the y direction, make sure that that's 0. In other words, calculate the equilibrium of the entire structure. I analyzed it as 3 separate parts, but now I can consider the structure as a whole. Now that I know what all the reactions are, I can consider it a whole and analyze the equilibrium, or I should say verify the equilibrium of the complete structure. So I challenge you to do that to check your work. Check the equilibrium of the entire structure.